Question 1. The figure below shows a transducer used in a medical ultrasound scanner. Explain why a backing material is used. So let's just remind ourselves how this system works. An electrical signal gets sent in through the cable, arrives at the piezoelectric crystal, electrodes front and back, so we get a potential difference across this crystal caused by this electrical signal. That causes it to start vibrating. It expands and contracts, producing some sound waves. This burst of sound waves goes off into our patient. Inside the patient, it might encounter some different boundary layers. At each boundary layer, it will be partially reflected back, partially transmitted. So we get a set of waves here that are traveling back towards our piezoelectric crystal. When one of these sets of waves arrives at the crystal, it causes it again to vibrate. The crystal expands and contracts as the wave passes through. This expansion contraction creates a potential difference between these two electrodes, which is sent as an electrical signal back through this cable, which is going to go off to our detector. After this first one's arrived back, the second wave will come and will cause the same thing to happen. And then the third wave will come and cause the same thing to happen as well. So this is the process we should be picturing inside our transducer. So we're talking about a vibrating system, and we've got a backing material near it. So hopefully our head should go straight towards the idea of damping. We want the piezoelectric crystal must stop vibrating in, I suppose, two fairly specific situations. One, after it produces the ultrasound wave. So it needs to stop vibrating quickly then after it produces the ultrasound wave, so it's ready to detect reflections. But also it must stop vibrating after detecting after detecting one reflection, and that's so it is ready to detect the next one. So there'll be some sort of level of resolution on it. If it bounces off two surfaces that are incredibly close together, we're not going to be able to distinguish that there's two separate surfaces. But to do the best we can, we want this to stop vibrating as quickly as it can after it's detected its first vibration. Part B. A beam of ultrasound is transmitted from muscle into bone. So it's going from muscle into bone. So I'm going to label them Z1 and Z2. Calculate the percentage of the incident intensity that is transmitted. So as we've just said, when ultrasound approaches a boundary, it's partially transmitted and partially reflected. And our standard equation here actually is about the percentage reflected. So we'll need to bear in mind that this is asking us about transmitted. We've been given the acoustic impedance of the bone. The bone's the material it's going into, so I'm going to label that as Z2. I haven't got the acoustic impedance of the muscle, but I have been given the density and the speed, which I can put together to find the acoustic impedance of the muscle. So this is going to be Z1 in a minute when I put it in my equation. The acoustic impedance of the muscle is just the density times the speed. So that's 1100 times 1600, which is 1.8 times 10 to the 6. We can just use the units above to save ourselves a bit of time. Then the intensity of the reflected wave over the intensity of the incident wave is the difference between the acoustic impedances Z2 minus Z1 divided by the sum of the acoustic impedances Z2 plus Z1 squared. So that's 5.3 minus 1.6 times 10 to the 6 over 5.3 plus 1.6 times 10 to the 6 all squared. So that's 3.7 over 6.9. Squared. Help. Which gives me a value of 0.29. So what that means is it's 29% reflected and conversely 71% transmitted.